And that will enable you to be able to replicate anything you want to replicate. So just understand how your code works, how your how your code works, how will I put it, how your class works, how your function works, then you'll be able to build on anything from anywhere. So today, Austin, right, will be taking us on another level of journey. I think last week we were able to round up on EDA. Am I right, Austin?
Yes. Yes.
Yeah. So Austin will be taking us on, I think we are starting machine learning proper this week.
Yes.
Ooh, I'm excited because that's what makes data scientist. So please try as much as possible, understand the concepts. There might be a lot of theoretical explanation. Just don't you can how will I put it? All the theories, there's also a simple code for all of them. So we will be taking you through the basics, which is understanding the concept before you start using the model, because model is nothing but a black box. And if there is no proper understanding of what is going on in that black box, you won't be able to properly interpret the results you're having, and you won't be able to properly apply that model to your challenges or problems. So please try as much, even me, I will although I have background in statistics, but no matter what, there is always an opportunity to learn. So please, and please, and if you have any question, please drop it on the chat so that I can look at it and try as much as possible. Even if it's something I'm not clear about, I can ask the facilitator to just go fast. Yes, it's fine. It's fine. And yes, so I think that's a little bit from me. So welcome to today's class, and hopefully you get your pen and paper and be able to note one or two things. So thank you, and over to you, Austin.
Yeah, thanks.
Thank you.
Yeah, so I was using two screens, one to share. Yeah, so I think I'll, yeah. I can, is it possible, can you see my screen, or is it this one?
Yes, your screen is up. Hands-on
Yes,
online
it's
training,
okay.
data science.
Okay, thanks. Yeah. So, yeah, thanks. So today will be, yeah, I'll be very quick with the slides. And also today, I think I would like to focus more on, trying to understand how algorithm works, like, how we can put some of these. I mean, so today I'll be doing some things that are very basic, but I can promise you that this would really go a long way, because, yeah, you want to, apart from, you want to understand how some of these concept works, the algorithms. Also, you want to learn, the implementation in particular. You want to know what's happening, how the algorithm works in general. So, yeah, on behalf of my colleagues, Faithful and Sean, I will be taking this week section on machine learning fundamentals and basic machine learning algorithms. I'll start from the slide, and after the slide, I go to the Python code. But today, the idea is we'll code from scratch. And why I decided to code from scratch is just for us to understand also how some of this concept works, how we can just construct simple algorithm, and it's applicable to any type of algorithm. Once you understand how, it's applicable to any type of machine learning algorithm. Once you understand in general how it works. Yeah, so what is machine learning? Yeah, of course, we always find different definitions. And so I'm not here to actually give you one standard definition, but one thing I always look out for is the machine learning itself is made up of two words, machine and learning. And we don't need any interpreter to tell us what these two words mean. One is saying machine, and the other one is saying learning. So let's begin with machine. Machine is just something that that does a particular task, something that that can achieve something, that can perform a task, make decision, or anything. And a machine can be anything, your mobile phone, your laptop, just an algorithm that you write, a function or anything that can perform a task, is what you come. Even you as human, your machine. because yeah, of course, you're human, you're a machine, because you can walk, you can eat, you can learn, right? You can do tasks as as normal human being. And the machine, the word machine here is kind of abstract word that can that can mean anything, as long as this thing just does this job and perform this task or something. And the word learning is also something you know um, quite interesting. The word learning there is you know is what we do in our everyday life. It's a kind of it's a present continuous statement. Word. You know, so it doesn't just say learn; it says learning, and just as we are doing now, as we did yesterday, as we are going to do in the nearest weeks to come and months. If you look at our lives from when we were kids until now, I can bet you that you have learned a lot and you're still learning. So when we say machine learning, you're just putting this thing together. You have something, that wants to learn how to do something, that performs a particular task, and things like that. And in the concept of machine learning, it just basically means we don't want to outcode something. Like we don't want to explicitly program something to do something. We just want that thing to learn how to do something, right? And that is basically what machine learning is. And how does this, how does it achieve this learning? So it's a kind of algorithm, that iterates through some kind of, already data, based on observation or something. And with this data, this algorithm or anything, tries to learn patterns and and try to understand the just trying to find what is peculiar, like what is very common to these things, and can perform the task. And this is something very it's closely related to how the baby would learn. Think about the baby today, probably um, you know what can I use as an example? Okay, a child that wants to eat, like this baby in the screen, um, you know, and the child just messes up everywhere, and somehow the parent says, okay, you can eat without messing up your place, and the next day the child tries to eat, you know, um, in a way that he or she doesn't, mess up the place. And the most interesting thing is you find out that this baby over the years would learn how to do this particular task, towards perfection. I mean, not 100% perfect, but I can tell you that the child would definitely one day, learn how to do this. Yeah, so my voice is echoing. Yeah, so this is basically, my voice is echoing. I don't know why. Okay, thanks. Yeah, so this is basically the idea behind how baby would think and learn. Most of the times they learn by correcting them. They also learn by just what they observe. Some kind of they just get used to these things. And yeah, so just think about when we talk about building algorithms that wants to learn to perform a particular task. The algorithm or just behaves like a child, makes mistake, get some kind of feedback. In the case of supervised learning, use this feedback as an added information to correct itself, and repeatedly the algorithm learns. And what are the so briefly, I think it's nice that I just talk about this concept, because also something that we, in as much as they are different fields, but I can promise you that they overlap, at different, at, at different place, something like that. And for example, what are the objectives of machine learning? We have statistics, we have computer science. Yeah, well, I could have included mathematics, but I mean, this is not something to debate. So when we talk about statistics or anything, yeah, but I can promise you mathematics also should be here, but I don't know why they include it. But I think machine learning, statistics, and computer science is something that is very, 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 very close. And usually people in this discipline, including math, I will tell you, can, or even outside this discipline as well, can do, can be very um, good in in machine learning, things like that. So the objectives are quite different, as you can see, and of course they all focus on different things. Like for machine learning, it focuses on just learning from data and to make predictions or decisions without explicitly being programmed. And for statistics, it's quite different. It wants to infer some kind of underlying some patterns or properties of some underlying distribution from data sample, and and it probably works with some kind of interpreting data and some probabilistic models. Computer science just focus on creation of applications of algorithms, to manipulations, then the store and storage, also communicate digital information. And the methodology also, as we see, typically machine learning just uses complex models like the neural networks and also large amount of data to train models. So that's the main methodology. We have data, we want to train methods on this data. On the other hand, we have statistics that wants to focus on interpreting models, right? Like hypothesis testing, some kind of experimental design, estimation, and some also kind of mathematical analysis. Computer science also focuses on just algorithm design, from data structures, computation theory, computer architecture, software development, and much more. For validation, how do we validate some of these methodologies? For machine learning is just we have the model, then we just want to know how it performs, right? Like we want to do a kind of performance on an unseen data that the model hasn't seen before, and we try to evaluate the performance of this model based on on the performance on unseen data. Statistics, there are methods that can be used to validate this model, such as confidence intervals, p-values. Also, they use hypothesis tests to quantify some kind of uncertainty. In computer science, you can see also it uses formal methods to verify correctness, analyze computational complexity, and proving algorithmic bounds. And the primary concern is to create models that learn from machine learning, create models that learn from and make decisions or prediction based on data. Statistics draws valid conclusion, quantifying uncertainty about observed data and the underlying distribution. Computer science creates efficient algorithms, data structure to solve computational problems. Now, this is very interesting because we see all of these different fields, what they do, and in as much as I think they are different, they often overlap. For example, machine learning is a subfield of computer science that frequently use statistical methods. And similarly, we have modern statistics that often employs computational techniques from computer science. So they're just kind of interwoven, and they intersect at some place. And what are the types of machine learning? Like kind of well-known, so the kind of, how can I say, the problems that are, that is very peculiar to machine learning. We have, three major types. Others are just built on these other types. We have supervised learning. We also have unsupervised learning, and we have reinforcement learning. So these are the three core, types of machine learning. And well, you see other types like, semi-supervised or something, but they are just built on these three frameworks. And for supervised learning, we talk about, so from the word supervised, it's very straightforward to know that you want to supervise the learning, right? You want to supervise the process, just like as we, most times in our place of work, your boss already knows, what you should do. That is, your boss already knows, um, so already there is so he or she knows the output of what you're expected to do, right? And you have to, do that thing, even though you don't know you don't know the output, but you just have to do it because you're working on it, right? And you get something, you're not sure if you have done the right thing, and you go meet your boss or your supervisor, or it could be anything. Maybe like I remember when I was also writing my project back then, you do something, you take it back to your supervisor, and the supervisor gives feedback, something like that. And, so this is just something very close, exactly, right? And you learn based on this feedback from, that desired output, which your supervisor knows. And as you can see, um, this is just basically what supervised learning is all about. We know the desired output, we know the output, and we want to ensure that we use this output as an added information to correct ourselves. It's like a feedback. We use that to correct ourselves, right? And just like I gave an example of a baby that is also learning. The baby learns by correcting, by correction. You know, the baby does something today, and you say, "Don't do this." Tomorrow, probably he or she does it again, and you say, "Don't do this." I can bet you with time, the baby would stop to do that thing. And because the baby has learned that this thing that he or she is doing is wrong. And over time, he or she has gotten feedback from the parents that what you're doing is wrong. So you just have to correct yourself. Don't do it. And this is basically how it works. And some of the algorithms that are very peculiar to supervised learning is standard linear regression, logistics regression. You have the k-nearest neighbors. You have the decision trees and random forest. You have the support vector machines. You have the naive Bayes. You have the neural networks. I won't go deep into all these things because of time. However, if I would share this slide, I'm going to attach links to these slides so that you can read more on how this algorithm works. And unsupervised learning is just the inverse of supervised learning. There is no desired output. You don't even know, right? You don't know. You don't know. You just want to use, your intuition of something to understand. Like you want to learn based on some kind of intuition about the data. And I give an example. If I imagine we have pictures of, let's say, pictures of cats and dogs. No, cats and dogs are really close. I want to use something that is very distinct. Okay, imagine you have picture of, let's say, cats and, I want to use another animal that is very distinct. Cats and mouse, no, dog and mouse. Yeah, dog and mouse. So dog and mouse. So you have pictures of dogs and mouse, scattered around, a paper, right? And we give that paper to a child. I just want to assume not a newborn baby, not a baby that don't know it, but a child that knows at least what this can be. And you tell this child, okay, can you in a way try to, can you try to can you try to identify, can you try to kind of group, let me use the word group, or kind of just form a cluster, just group, these images. I'm not going to tell you, the number of groups, this image, just group them. And I can promise you that the child should be able to know that, all the pictures of dogs would, would fall into one group, and all the pictures of mouse would, mouse would fall into another group. And what is very interesting about this unsupervised learning is sometimes you don't even know, the physical interpretation of, of what you're trying to cluster, like what you're trying to group. You just know that there is something peculiar about these things, like dogs, for example. There is something about dogs. Probably you say dogs are bigger in size, right? They have this kind of, they have big, big. So if you compare a dog and a mouse, the difference is very clear. Dogs have longer legs. I mean, compared to mouse anyway, mouse would definitely have smaller legs. Even in size, you can be able to do these things. So, and some of the well-known algorithms are the anomaly detection. We have the K-means clustering, hierarchy, clustering. We also have the density-based spatial clustering of application with noise, DBS CAN. We have the principal component analysis, and we have neural networks also. Well, I can promise you, I would also attach some links that you can read about these methods, right? The idea of the slide is just to show that these are the well-known methods. And we have reinforcement learning, right? And this is slightly different from supervised and unsupervised. Basically, what it does is, it discovers, using some kind of trial and error technique, and what it does is that, so the aim is, to use this trial and error and also focus on action that yields the greatest rewards, right? And it's quite tricky because there is really nothing, you just want to create a kind of environment where something like, you're not telling the person to do this thing, but the person just does something just happens, and by carry out an action, and probably the person doesn't even know if this action is good or bad, or right or wrong, but the person, the agent rather, just notices that, okay, which of these action, like, always yield, a kind of reward, kind of, compensation or something. Think about like a parrot, the way parrots learn, parrots are really smart, right? And, of course, you still have to teach a parrot how to, talk, or, make some kind of, funny reactions or something. Yeah. And when the parrot says something, and you give the parrot a kind of, nice treat, like, something like a food or something. I don't know what parrot likes to eat, but just think about, tell the parrot, okay, just do this, and the parrot just do a kind of, something like just guesses or do something, and you reward, you reward the parrot, and over time you notice that this parrot just begin to memorize, some of the actions that it had, that like in the past it had, done, and that has, that yields, good rewards or something. And the primary component is, we have an agent, that is what wants to learn, the learner. We have the environment, what it interacts with, and we have the action, what that agent can do. And the objective is the agent have to choose the action that maximizes the expected reward over a given amount of time, right? And it's very simple. Sometimes you see really smart dogs, they know when to press the kind of button that tells the owner that they want to stroll, or they want to eat, or they want to do something. These are just basically, what they do. They do something, and you give them nice treat, they learn from it. They try to focus on some of the actions that, the action that makes you reward them. So they want to maximize that, that reward. That's the goal. And we have some algorithms, Markov decision process, Q-learning. We also have the deep Q-learning. Like I said, you can find a lot of this algorithm online, where we can also learn about these algorithms. And now, why do we use it? Because we want to extract patterns. from we have like think about you have large amount of data. You cannot start analyzing data line by line. It doesn't make sense because you can spend weeks. Imagine you have tens of thousands of data, and you can just think about writing a nice algorithm that can learn patterns from this data, and you can try to know or what is very peculiar to this data. What are the interesting things about like what can this data do? How can it solve problems? And humans typically, even though we are very smart, we cannot do a certain threshold. We can't do more than our capacity. And even as we can see, what computer would do in minutes or seconds, human would take a lot of time. Not because of the computers are smarter, but because humans are smart in a way that we can write even smarter algorithms that can make make task or job very easy, right? And of course, machine is just a dummy thing. It's what you just garbage in and garbage out. It's what you give to the machine. It's going, that it could do. So without complaining, as long as the computational resources are available, and the machine will achieve that task. And so some of the use case application, we have email spam filter. Sometimes we check our email, you see that some of the emails are in the spam already. It's just with the idea of um, classifying if an email be a spam or not. So that is very close to the area of natural language processing, where we have this, we have words or sentences, and the machine learning algorithm learns which sentences can make that email become a spam or not. We also have recommendation systems, self-driving cars, finance, image recognition. For this, we will do this next week. This will be the project I plan to do next week for our deep learning class, and also competitive machines. So I'll be very fast now with the slide. So typically we have this image. This is how, like the first half towards the left, we see that it's just about data preprocessing, nothing more. We want to prepare our data. In the middle, we apply the machine learning algorithm. Towards the end, we just, we deploy the model that, the model that performs, very well, right? And that's just basically the pipeline, like typically machine learning pipeline. You create a model, you have your data, you do the processing. Like my colleague also mentioned last week, you have to understand the data, if it's from the business side or from, if it's a business data, you have to understand the business side. If it's educational data, you have to understand the educational applications. Any kind of data, weather, you also have to understand. And basically that's just it. So now think about your boss asks you a question. Your boss gives you a task to develop an automated decision maker on whether to give a potential client credit or not. So which is in banks, like, we know banks can give credit or not, but that not every bank, every bank will not give loan to everyone that applies for loan or credit or something. And this can be due to several factors, right? But just think about the problem. So your boss says, okay, just create a kind of smart automated system that can tell me whether to give a client a loan, a credit or not, right? And what comes to your mind? What question are you trying to answer? So what is the problem? What is the question? How do you solve this problem, right? This is where selecting the appropriate data feature comes in. So feature are just the the kind of, how can I say, think about okay, for example, so you want to give someone loan, credit. what do I need to know about that person? So what are the qualities of that person I need to know, right? And this is where kind of feature, selecting. Of course, we have to select the data. We have data, but what kind of data do we need? Because we can't just use any data to answer this kind of problem, right? And basically, what we want to do is, what can influence such a decision of giving this customer the credit or not, right? And industry experts or domain experts, such as financial advisors like loan officers, credit analysts, or and so on, they can be very helpful in this process because they understand the key factors that contribute to credit worthiness, right? And but as you can see, you have this individual measurable property. Already, you know that, okay, this individual, you want to, but you cannot know everything unless, you seek, advice from, industry experts. And it's also very important when you're solving a problem because you want to know, the most, interesting information for the problem, right? And you want to extract these features. You already have the data. It could be a lot. It could be thousands of variables, but you don't need all, right? You just want the most important things that can solve that problem. And this is where feature extraction comes, right? You want to extract the features. In the case of the credit card we talked about, think about it. One thing that may come to your mind would be, okay, before I give a customer a credit or not, I want to know the customer's age. I want to know the employment status, right? I want to know is our income, like monthly income. When I mean income, I don't mean salary. I mean after every expense, the income. I also want to know maybe the credit score. Maybe in the past, the individual has collected credit and paid back. Then because if you have collected credit in the past and you have paid back, you have a score, right? Imagine someone with a very high score. It means this person, can be trusted, because imagine someone has a very low credit score. It means this person cannot be trusted. We can also think about the amount of money this person wants to loan. We can also say, okay, I want to know why this person wants to collect the loan, the purpose. I also want to know maybe existing debt of the customer. Maybe if the customer has some debt somewhere, he or she has not paid, and he wants to collect another credit, then I would suspect that person, right? Or some kind of payment history or number of dependents, right? Education level status. Probably you feel like, okay, people who are more educated are more likely to return the loan than people who are less educated, or maybe marital status, or probably people who are married, have more commitment or, something, and so on and so forth. But there is always a problem, when you want to analyze these large variables, like I just mentioned now. But the question is, do I really need all of these variables? Because I've mentioned I think almost 11 or 12 now. The question is, do I really need all of these to decide if a customer takes a loan or not, a credit or not? And this now boils down to takes us to what we call, how can we reduce the amount of resources required, to actually still solve that problem, because we want to keep it very simple. From some of the examples I've listed now, you can say, okay, forget about it. I think I will just focus on credit score. But there might be a problem because what if it was a first-timer, right? Someone who has never collected loan before, and the person does not have any credit score. So is that enough? No. But of course, if someone would have collected the credit before and maybe paid back, then that can be added. But it might not really generalize unless you put a strict rules that the person must have somehow collected loan before, which is even usually the case. Like in developed part of the world, like here, I remember when I wanted to rent my first apartment, there's something they ask for. It's called shufa. So I think that place is where they check if you are owing debt or something, or maybe or something. And the question is, well, what if I have no records or something? I mean, I'm just saying, and there are other things you can consider. Okay, let me know also what the person earns, income. Probably it would be nice to know, because someone earning like, let's say, 50K, I don't want to, I mean, I'm not saying whether it is Naira or dollars or something, but just 50K could be any currency. And the person 50,000. So yeah, 50,000. And the person wants to get a loan of, let's say, 1 million. And you begin to wonder, how is it possible that this person can pay back this loan? And probably, you want to give the loan within a specific period of, you want to give the person, a specific, timeline to pay back. And this person also would surely continue to spend money, have expenses, and you might feel like, okay, I think I want someone who has, or you can also just put the ratio of the amount the person is asking for and the amount he or she is earning. If it's more than, let's say, if it's more than half, or if it's twice. I mean, if it's more than twice what the person earns, then sorry, I'm not going to give that person loan, right? And a lot of things, I mean, I'm just saying. So these are some of the basic things you meet in everyday life. You say, okay, you're a data scientist, and the question is, what do I need? What do I need to solve this problem? And yeah, so like I said, so when sometimes we have lots of features, we want to reduce them, right? It could be the case that maybe there are two variables within, what you are considering. I mean, two variables that are very, very, related. I give an example. Now, think about someone income with, let's say, the loan amount. There could be some kind of correlation, because intuitively, you can say people who earn more are likely to request for more loan, right? And also, people who earn less are likely to request for less loan. And this is because the person who earns more believes that he or she earns more. Of course, he or she can ask for more loan, higher amount of money, because that person is confident that I earn more money, so I can pay back, right? And someone who earns, low, like smaller amount, can can afford to pay back. So think about this option. So if you are trying to do a kind of feature selection, you might say, okay, these two might be redundant in a way. And why don't I just kind of squeeze them into into one into one something, right? And yeah, then it turns out that at the end of the day, I can just reduce this, like I'm just saying, shrink these two into a kind of, like, you're kind of doing a dimensionality reduction, right? And because you are transforming large set into smaller set. I just use these two cases. There could be even be more than two. There could be 3, 4, 5, right? And you want to know what is, these things can be very related in a way, right? And what's the point using all of them if they will just be redundant? It doesn't improve the model, whether I remove one or not. And usually we want to keep our model simple. Okay, so how do you prepare our data? Cleaning, my colleague talked about this last week. You also need to know the units of the variables. For example, like age. Now, age has no unit, right? Or if it's, no, well, it could have, let's say years. Yeah, of course, you cannot give, someone cannot. So usually age is denoted in years. Employment status, let's say, maybe no unit. Maybe it's a kind of binary thing, like 0 for unemployed, 1 for employed, or 2 for retired or something. Or maybe income, you want to know if the person earns in Naira or dollars or pounds or any kind of currency. Very important, missing values also, we talked about that. When you have missing values, what do you do? Especially if it's a lot. And there are several ways to accommodate or try to make up for missing values. If it's very few, you can remove it. Or if it's a lot, you have to think about how you can try to get more data, or find a way around. And you also have metadata, data that describes data. Like you want to know all the information about this data. So very important. And so the goal is you want to minimize the error on the training data. So the concept of training data here, think about it as this is the data we want to use, we want to train our algorithm on, because we need to train the model on the data, right? And when during training, we want to ensure that the error is minimal. And when we talk about error here, the error here is how far is the predicted value from the ground truth, that is from the original, from the real value, right? This is the case of supervised learning anyway. So we want to minimize this error. We want to make sure that the prediction is not far from what we would expect. And the training data is the data used to train the model. So like I said, and so we'll talk about that also in a moment. And so let's just briefly sketch what linear model is. So yeah, there are different types of model, but when you talk about linear model, from the word linear, it means the relationship between the predictor, and the predictor and predicted is linear, right? And it's just saying, okay, you have a two-dimensional graph or a plane, and you draw a straight line where each axis denotes, the two different variables. We'll talk about that also in a moment. Yeah. Also, this line can even be a way to classify objects. You can say, okay, the ones towards the upper left belongs to one class. The one towards the lower left, right, belongs to the lower class. Yeah, that's just for linear model. It's just very straightforward. But because today I will be coding from scratch linear regression. That was why I talked about it. Okay, quickly, nonlinear model is just the inverse. Of course, something that is not a straight line. Exponential, some kind of polynomial, like second degree, more than like degree 2 or higher. Some kind of any function, as long as it's not linear, then you say this relationship is nonlinear. Okay, and yeah, there is also an important concept called overfitting and bias. These two guys are something that you really have to understand, because if you don't understand what overfitting, or when you are in this scenario, then it's a problem. Well, we can see the definition on the screen. However, I won't. You can just read it. But so I just want to go into something that is very just an illustration. So, what is overfitting? What is bias? And so I will just give maybe an illustration. Yes. Now, you have so we have two students. Both students they have an examination. Let's say physics exam, and one of the students, of course, they would read, right? Yeah, they would read. But you notice that one of the students is just cramming his or her notes. Cramming notes or past questions, related to the, to the subject or something. Just cramming word for word, word for word, word for word. Like this student is just cramming. She's just cramming. He or she doesn't even care. The person is just cramming word for word. And you know what I mean when I mean cramming? So the person is just cramming. And, there are some subjects you don't cram. There are some subjects you cannot cram. Well, I'm not into, I'm not an art student, even though for other disciplines that don't really have much of, calculations or, of some formulas or things like that, or some things that have to do with experiment. But I can bet you, overall, when you read, you don't want to cram, regardless. You just want to understand. For example, definition. You want to just cram everything word for word. But let's even talk about things that are more technical, like physics, things that have formulas like math. And this student just begins to cram, just cramming the questions, cramming the note, everything, just cram. On the other hand, the other student doesn't just cram, but tries to understand. Just reading to understand, right? So in the comment section, can we type? And okay, now before you make a comment, now I've given an example. One student is just cramming. The other student focuses on just understanding, reading to understand, right? not just cramming formulas or cramming the past question word for word, but solving them, applying the formulas where necessary. Sometimes before you apply formula, there are some parameters you need to actually calculate. So this student focus on just understanding the concept of that problem. Who do you think would pass the exam? Like, who do you think would perform better? Let me just put so who do you think would perform better in the exam? And mind you, exam questions are questions that these students haven't seen before. So in the comment section, can we just type? So you can just say student that cram or student that understands, that read to understand. In the comment section, can you just type who you think would perform better? Who do you think would perform better? Exactly. So apparently the student who reads to understand, which is always the case, someone who focuses on just reading to understand tends to perform better. And it's not, rocket science. And now let me bring this concept back to, overfitting. In the case of machine learning, your model is just cramming the data, just like this student, just cramming. Doesn't even learn any pattern or try to understand the data, just cramming, trying to perform very well on the data. That is the training data now. And when the person goes to an exam hall, the person meets a question, the student meets a question that he or she has not seen before. I'm telling you, the student will fail woefully. Compare the performance between, what he or she has read, crammed, of course, the student has crammed everything. The student will perform very well on that, on that aspect. Now let's go to the exam question where the student haven't seen before. The student will perform woefully. Let's say the student is very good at cramming and maybe, he or she is with friends, they are testing themselves, if they are, ready for the exam and they start asking questions, based on, what the person has read. I can bet you the person can even score 100, or even 90 something. But now when the person goes to the exam or come across question that he or she has not seen before, the person might even just maybe score the person can even fail. Or maybe, I don't want to give the student mark or something, but I know the person will not perform well, surely, right? Well, unless if the student have crammed and at the same time try to understand the complexity of the problem. That's even a different case. But in machine learning, is either we're here or there. It's very tricky. And that is what they call overfitting. That is what the student have just done. And that is what our algorithm also will do in terms of, machine learning. The model is just cramming the training data. And now after training the model, you want to test the model on the data that this model hasn't seen before. Then the model will perform very woeful. So the model would just, the model would not even perform. So the model would just, any word just to describe, bad performance. On the other hand, a model that tends to, understand the data, understand the pattern, the most important, patterns of that data, would perform very well in an unseen data. And this is basically what we always want to achieve generally in machine learning. You have data, you want to train a model on the data. You don't just want the data to start cramming. You want the data to understand. That's what we call patterns, understanding patterns. And when you take this model, you feed it with an unseen data, a data that that the data has never, the model has never seen before. The model will perform well if indeed the model has, the model has actually learned. Now let's go to bias. Bias is also something that is very close. But what's the difference? I'm still going to use this student as an illustration. So let's go back to where we started from. Still the same physics exam, both students. One crams and the other one reads to understand. But now it's a little bit different. The student who crams is not just cramming, let's say it's not just cramming, but cramming another subject, let's say chemistry. The student, no, I want to use a completely, okay, let me use chemistry because it's somehow close, but it's still outside of what we might expect in certain areas. The student starts to read chemistry, cram chemistry book, right? And the student have, physics exam. What do you think would happen? Not that not only that the student would even, perform woefully, what the student would write would be far from what we would expect. You understand? For the solution of the physics questions. Now, I know it's a bit tricky. Now, let's go to the students who read to understand. Now, of course, the students read to understand, but the student is reading another subject, chemistry. The student has a physics exam, but the student is reading to understand chemistry. You see the difference? Although the student, is doing the right thing, in reading to understand, but the student is going outside of what we would expect. Because the student ought to be reading to understand physics, not chemistry. And when the student goes into the examination hall, the student would, of course, I expect the student to write something nice based on what he or she has learned. Read to understand from the chemistry course. But what that student would write would be far from what we would expect, which is like, typical, solution to typical physics problem. And in this case, we say there is a bias. Not that, apart from the performance, they are just moving far away from what we would expect. And we don't want that. We want to be very close to what we would expect. I believe this illustration would actually, you can read through the slides, but of course you would understand from my illustration. The bias overfitting occurs when a model fits the data more than is warranted, which is exactly what I've just said. The student is just fitting his or herself to his notebook, to the data he or she is reading now, not even trying to understand, trying to think outside the box that, okay, what if they change this value or change this parameter? How can I solve it? Bias is the error from erroneous assumption in the learning algorithm. So we're expecting the algorithm to, so we're expecting the algorithm to predict results that are not far from what you would expect. That's the concept, that's the idea. We don't want the algorithm to be far from what we would expect. Because even though you are building a model, you expect the model to do something. You don't always want the model to just predict anything far from what you would expect. And this is where bias comes in. And it can lead to underfitting. Just like the student now that I said. The student just, the student did the right thing, like, by reading to understand, but it's far from what we would expect. And that solution might not even, meet up to what is expected. And that is what we call underfitting. You underfit, you're not meeting up to the expectation. Yeah, and a typical case could be you have data set that are, kind of complex, like, and you want to fit a linear model on that data set. It will not work. It's going to lead to a kind of high bias because it's the straight line, the linear model might not be able to capture the relationship properly. And this is an illustration of what I'm actually talking about. So on this side, we have overfitting. You can see the blue dots are the training data. You see how the training lines are just connecting. This is what they call overfitting. The algorithm is cramming. And you see the orange dots, they are the test set. They are the unseen data. If you calculate the error here, find out that it's just overfit. You can see the error on the training set will be 0 because the line connects all. And I'll talk about the error in a moment when we start to write our algorithm. And the orange line, you see that it will perform very bad on the orange dots. So in this case, and this is just a case of that student, does very well on the exam, on the questions that he or she is cramming, and when it gets to the exam question, he or she cannot even do it. Now, underfitting is also what I just mentioned, in the case of like high bias, you have, of course, you don't expect this training. So the error from the training set would not be far from the test set, but it's far from what we would expect. Maybe like the error is kind of high. right? We are expecting something very low, and we say high bias, high bias. But this someone is raising, someone raising. Okay, I'm going to give you a few more. And this one here is a balance. Is something kind of optimal. We are not underfitting and we are not overfitting. We are just at the middle, right? And this is what we would always expect in our model. Okay, and this is also, a combination of bias variance. You see low bias, low variance. Our model, we always expect to be here. Low bias means, like I said, we want to be very close to what we would expect. Low variance means we want to actually learn patterns from the training set. We perform quite good on the training set, not like 100%, because we cannot be 100% perfect, because we are just trying to understand patterns, and we use this knowledge on unseen data. And I expect to also perform well. Low bias, high variance, you see the difference? This is also, in this case, we are actually close to what you would expect, but there is high variance. I mean, like, you are kind of, you are doing very well in the training set, but you are going out of the, of the test set. However, something still close to what we'd expect, but because the error between, what the training set and the test set is very high, then it doesn't make sense. We would expect not to have really a good model. So we always want to keep this down and keep this down. High bias, low variance, you see, we are even outside what we expect. This green shaded part is what we would expect, but we have low variance, and you can see the variance they are relatively packed together. This is because the the model, the performance on the training set is very close to the test set, like than in the unseen data. But we are still far from what we would expect. We don't want that. This is even the worst case. You have high bias, you are out of what we would expect. You are still not even learning the patterns from the data. Can the person who asked the question ask the question? Someone raised his hands. Okay, in the absence of that, let's move on. So to end it all, I think I'm not done yet. So we minimize the error and we make sure that the error in the unseen data is close to the error in the training data. Okay, you can ask your question.
Thank you. I sent thank you very much. I sent a message to you directly. It was about the variance bias concept. Yes.
Okay. You mean I should talk about it, or?
Yes, sir. Please, can you just?
Okay. So, okay, thanks. So there's always a trade-off, right? But in the end, you always want to ensure that you are here, right? And what is the trade-off? The trade-off is that in the course of trying to reduce one, might actually overshoot one. In the course of trying to, overshoot one, you reduce one. However, and this is where, hyperparameter tuning comes in. When you start training your model, of course, machine learning model is basically, you have to do some hyperparameter tuning. You have to carry out some experiment. You have to check which one performs best, because it's a kind of black box, right? And usually we can't tell which works unless you go through the kind of model selection process, and things like that. I can tell you. So the trade-off is that ensure that the model, you build a robust model that would output what you would expect. However, the performance on the training set, that is what you use to build the model, and what you would test the model on, which is an unseen data, should not be far from each other. You don't want these two to be far from each other, and you don't also want to be far from what you would expect. If you build a model to classify dog, and this model is classifying cat, the model is doing something out of what you would expect. High bias, right? We don't want that. So always try to keep it low. Don't worry, we can probably during the course, as you move on, begin to understand this concept, where you begin from your results, you would know what is happening to your model. So be very careful. And the variance here, like I said, so I've been talking about error. Of course, it's just the sum of square errors and kind of average, want to average to this error. And it's just the normal formula for variance, right? You want to see how this, the output, performs on the ground truth, on the real, on the known output. And you want to sum it, right? Because we have several samples, right? You want to sum over all the samples and want to find the average or something like that. All right, thanks for the question. So we keep it simple. You want to keep your model simple. There are also techniques, to always use to evaluate your model, to estimate the error, right? You want to see where you are. You want to know if you are balanced. You want to know if you're not on the high bias side or the high, overfitting, high variance side. And there are also regularization techniques that can also help, because when your model begins to get too complex, for example, this model, you can see the non-linearity there is too much, and that is why the lines are connected. If you apply a regularization technique, you can penalize some of the parameters that actually adds non-linearity. And at the end, it might just end up linear. And those are just regularization techniques, right? So yeah, there's also what we call data snooping, data dredging. So in this case, we want to, maybe we are in the, we build a model and, it basically occurs when you use a data set repeatedly in a kind of maybe exploratory analysis or model selection. And this can lead to, a kind of overly optimistic performance. So because it's something that the data is contaminated. It's just like you build a model, and you are using one particular set of unseen data to test. No, it's wrong. Once a data set has been used to test the performance once a data set has been used to test the performance of a model, it should be considered contaminated. We don't want to use it again. We want something new. Because that is what actually makes you know that the model is robust. The model is working to any random sample of unseen data. And this is what we call data snooping. So always try to avoid that. Okay, how do you interpret your result? You have to validate it, through cross-validation or test set. Like, you have to split your data. You use one for training. You can split into 2 or 3. Then once the test set has been used, you must find a new data. Okay, now we are done. So we would go, today we would be, talking about linear regression. We'll be at coding linear regression. And the reason why I chose to do this is because I want us to understand how some things work, right? And last week, my colleague took us through, some things about, about data exploration, and today we'll be using this data set. It's called the, it's a weather condition in the World War II data set. It's a data set about the weather condition of World War II, something like that. So I put the data to GitHub. This is the data. But don't worry, this is on GitHub. For some of us that are asking, how do we get data set that are not, inbuilt? So this is one data set, you can put it on your GitHub. So this is my GitHub page. I just uploaded it. And you can see it's a CSV file. You can even see the extension. You can see the extension. Is my screen big or small? I think I have to increase it.
I think it's fine.
Is it okay?
Yes.
Okay, thank you. So we want to get this data and quickly, because this data is hosted on, on GitHub or some kind of, domain, whatever. It's not in our local machine or Python inbuilt. There is this widget function. Sorry, I'm going to share my code after this class because I'm writing the code from scratch. So I just copy paste this. So this is the link. You can see this is the link I just searched for. So I want this to run it. It would load. And yeah, it's done. So just come here and refresh. Click on refresh. You see the data is here now. Now we have our data. Let us, from last week, if you notice, you want to load the data set. what do? We just, we import pandas, if you remember pandas. And, we can just read this because the CSV is already here on our computer. So we can just, copy the path or whatever. No, I don't even need to. Okay, good. So let us print our data. Remember,
Hello, Austin.
yes?
Please, someone is asking for the link to the data set. So just paste it on the chat.
Okay,
That's
okay, thank you. Okay, no
yes,
problem.
data set. Thank you.
Yeah.
So
Okay,
maybe they can follow.
Because where's my chat? Okay.
So
But not to worry.
just press
Yeah,
escape. Just press escape.
yes.
It will bring
Okay, yes,
about all your icons. So then you
yes.
can. Yeah.
Yes, I will still share the notebook. Okay. But yeah, this is the link, the CSV file.
That's fine. Thank you.
Yeah, so it's just the data, I got from Cargo. There are lots of, open source data. So quickly, because we don't have much time, we want to predict. So what's the question? If you look at the question here, the data set contains information on weather conditions, snow, temperature, precipitation, a lot of things. The question is there a relationship between the daily minimum and maximum temperature? Can you predict maximum temperature given the minimum temperature? So this is what we want to model. So we want to do a simple linear regression. And why I want to do this is not just because I don't want to do big things, but just to take us through algorithms. So to be very fast, because already we know, we can just check for missing values, right? Can check for missing entries, as usual. And we want to print. Already we have our weather. Last week we did this, so you just say is null, Then remember I said you are going to sum it so that you can know my colleague, so you can see these are the variables. However, these are the two. We want to predict the maximum temperature from the minimum temperature. So they are not null. They are not null values. So what we want to do is, we just need those two. We want to extract what we need. We don't need. So let's create a new data frame. We just want to extract the two minimum and maximum temperature. That's all. So minimum temp, because that's what we want to use for our regression model. Maximum temp. So that's how it is. So I didn't just formulate it this year. So this is how just extract the. So let's print. Let's see our valid data. .head 5. Okay, yeah. So we have our valid data, and let's check if let's check the data type. Print. Remember the last time we talked, you can check data type by using this, the types, right? And you would know, okay, float 64 is good. Must be numeric at least. Otherwise, our model cannot work with, strings or something. So let us quickly just, let us do some peer plot. These are the things we did last week, right? This is just like the preprocessing stage. Want to import Seaborn as SNS, and we just want to do a peer plot. It's just a peer plot, yeah. Valid data, yeah. Okay, so now we are, okay, the peer plot is supposed to be small. Yes, so you can see this is the main. So remember the peer plot. It shows the the correlation graph. That also gives the it shows the kind of distribution, how their relationship, and we can see that minimum they have this kind of linear relationship, right? It looks like as the it looks like as one is increasing, the other one is increasing. So, but it looks like if we have a very low temperature, we have very So let's go back to the question. So can we predict the maximum temperature given the minimum temperature? So, for example, in a day, can we predict what the maximum temperature would be if we know the minimum temperature? Maybe in the morning or in the afternoon, the temperature was at minimum at this time, and in the night, the temperature tends to shoot really high, and it shows a kind of direct relationship. So we want to build a linear regression model. We want to build a linear regression model. And what do we need? Remember, to be very clear, we need, a kind of, so it means that we want to build a model, want to build a linear model, which is like a straight line. Remember, a linear model is like a straight line. We want to kind of formulate a linear model. So what we want to do is want to select the features, and target. So in this case, the feature is the minimum temperature, because we want to use the minimum temperature to predict the maximum temperature. So let us put the valid data, put the minimum temp, just like X and Y. Then we have the Y as which is what we want to predict. Maximum temp. So let's so basically what we just happened, you see that what you just see is, this is for the minimum temperature and this is for the maximum temperature. So let's just try to show the first four values, or rather, I think this is it. Oh no, it's going to be an error. Yeah, I think the first four columns also. Yeah, so we can see the first four values of the minimum temperature, and we can see the first four values of the maximum temperature. Now, remember, when we are building our model, what do we want? We want to split our data into training and testing, right? That is what we want to do. And there is a package. There is a package called train test split from sklearn. It's also a library from model selection. Import train test split. So now, once we import it, this is how it works. It takes a kind of a tuple, X train, S test. So this X train is what we use to train our model, and this is what we use to test it. Remember, when you train a model, you want to test it on an unseen data. So, and this is the output. I mean, this is the maximum temperature, the Y train, Y. So once you see Y, just know it has to do with output, the label, right? This is what we would use as an added information to ensure that the model, predicts something very close and not too far, like what we would expect. So I can just copy this train test split here. I'll put my X, I put my Y. So what it will do is, this X is what we have here already. It's going to split it. So I can put, because I want to split it into train and test. I want to use 20% for the test and 80% for the train. And the random state is equal to 23. So let us print. So I think I can just, because of also time too, I'm still not going to be after it. So let me, okay, sklearn. Oh, no model sklearn. Okay, sorry. It's supposed to be, yeah. Okay, so now remember, initially the data we had, what was the number of data? Okay, yeah. I didn't even, the data was about, okay, I can check the shape from here. Let's check the shape from here so that we'll know the original amount of the data. Oh, we're starting the wrong thing. Okay, we had about 119,140. And now we have split the data. So for training, we would use 95,232. And for testing, we want to know the performance of the model on 23,803 samples, right? And so there is something I would quickly just, in my other note, so which I want to also quickly paste also because of time so that I can also explain. So what you see here is, this is the kind of linear regression model we are talking about. In this case, we have the X to be our minimum temperature, right? And you have the Y to be our maximum temperature. You want to use this information to predict this information. And the idea is just to draw a straight line. And you see these red lines are just the distance. But mind you, when you're training a machine learning model, it doesn't automatically just arrive at this line at the goal. It goes through some kind of process, an iterative way. It can even start by a straight line like this. And it tries to check the error. These are the error. You see, model, this is a data point, but the model predicts this point. So if you check the error, we want to ensure that the error is very minimal. If the line goes through all of these points, you find out that the error will be zero, because this distance between the predicted value and the ground truth, that is the label, the original label, you see the difference. So you sum all of these difference, because these are different samples. So we just want to find the average error. This is the formula. This formula is just an equation of a straight line, right? And this is basically what we want to do. We have some linear model that has this parameter B1, B0. We already know this. X is the data point. And we want our model to learn this parameter. We don't know this B1 and B0. So B1 is the slope, not just is the weight. So let me just use the word weight. It's the weight parameter. So it tells us how fast this line is changing. So it gives us, it tells us the slope of the line at a particular point. That's the weight. Usually we use the word gradient or slope in simple math form, but of course that this is in machine learning, we always refer it to be the weight. It's the weight. So it's the weight on our predictor. And the extra B naught here is a kind of it's a parameter that makes the model more flexible, and it's the bias term. Usually it's always the intercept on the y-axis. So we want to code this, and we don't just want to code it. We want to write an algorithm for this. So how do we achieve this? What are we doing? Where do we start from? What is the concept of algorithm? Like how does my model want to learn? So here we have this algorithm. I just wrote the algorithm. So this is what we want to do. First, remember, this is the model. This is the model. Yeah, this is the model one. We don't know B1, we don't know B0, but over time, the model will learn this parameter. That's the idea. We are going to feed this formula, this X. Just think about this X. You see this X here, they are just data points. For example, this is X1, this is X2, this is X3, this is X4, right? Up to I thought that had the shape now. Yes, up to 95,232. So in this place, we have 92,232 points, all these points. And now we have to initialize this parameter because we don't know it, right? We don't know it. We want to initialize it, of course, because we have to start from somewhere. So the first step will be to initialize. We have to initialize parameter B0 and B1. It's just to any random number, be to 0, or can sample it from normal distribution or Gaussian distribution. So, and now the forward pass. Now, this concept is very important. What is the forward pass? Now, think about the forward pass as some kind of random guess, right? Because we have to start somewhere. Just think about like a child that is learning. Most times a child will always just want to guess. And with time, using this like, correction, kind of this supervision concept, then the child begins to, adjust itself, adjust herself to learn to do the correct thing. So we are just doing a forward pass, based on this initialization, random guess. It's going to output some kind of y hat. This y hat will be the predicted value. And the question is, how far is this y hat from y? Y is the original value. This y you see here. Sorry, I'm going up and down. So these are the predicted, these are the original y's, because this is the input. We want to use this to predict this. So when your model outputs something, we want to ask, how far is it from this, ground truth, which are the, the original label of the data. So in this case, we want to ensure if this is the original point and your model is predicting this point, we want to ensure that the distance between this value and this value is small. So we want to minimize the error. And we do that by, some kind of cost function. You can see this is very straightforward. You see y minus y hat. So this y means this y is the original value. It's the original value. That is this this one. I mean, as an example for the first sample. And this y hat will be the predicted value. So we have to get the difference, square it, and yeah, I think So yeah, this is just for a sample, and overall we want to do it for each sample, because this point you see here, they are for different samples. We cannot just consider only just one sample. We want to sum all the errors for all of the samples, at least just like an average error or something like that. And so in this case, you see that we just sum it. This formula and this formula, they're just the same. Only thing is that this one is just taking the average, right? And this is what usually always, this formula is just your formula for variance, only that, I mean, there's a difference. Here, we are not working with the mean, like we are working with the prediction. So it's a kind of sum of square error. I mean, you want to know the average, right, of the sum of square errors. So because this is the error, this is the square of the error, and we sum the error, the average, as the cost function. It is this cost function we use to calculate the gradient. There's what we call gradient. So, and the gradient is, we want to know how far, like we want to see how can we nudge this parameter. The parameter here is B1. Oh, it's supposed to be B not B. Okay, I think, yeah, sorry for the sudden change in notation. This is what I will use to write the code, but I think this should be beta 1 and beta naught, so that it's consistent with what we have here, and also here. I think I just wrote this for algorithm's sake, and I just messed up. I missed up the whole thing, because yeah, usually B is better to write codes like than the beta. So please, the B1 here, I'm going to correct it when I send. And yeah, okay, I think I was still trying to stick with this notation, and then suddenly I just switched to beta. Yeah, but whatever, beta, B in this context, they are just the same. And what did I do here? Yeah, so when we get the gradient, then we will update the parameter, because this is the parameter we want to learn from the model. And we repeat the process, and the model will converge. Yeah, this is supposed to be. Sorry, I guess this should be in a kind of something so that it comes out in a math mode. Okay, yeah, it makes sense now. So yeah, this is, in general, this is the formula we want to predict, and we want to estimate. Oh, this is wrong. This is supposed to be, oh God, I'm sorry that, yeah. So basically, this is just what we want to achieve. We want to create a linear model. So let's start, and it's very straightforward. So I'll be very fast. and I will try to explain everything, right? So NumPy as NP. So let's start with our algorithm. So let's create a class, a linear regression class. I'll be using class, right? And oh, okay, I didn't write it up. Yes. So and now let's pass. So let's go to our algorithm. It says initialize. We want to just random because of course we need to get an output first. Then we can now start correcting the model to perform well. So we want to initialize parameter b0 b1. So we can do that here. We can quickly say self.b0. B0 here is the bias. And we can sample from from a normal distribution. Doesn't matter where we sample from. At the end of the day, it might converge. But if you are dealing with, I can just also because of time. So we sample the second parameter, our B1. This is the bias. This is the intercept on y-axis. Or let's say I don't want to use y-axis on the maximum temperature because we are not dealing with y maximum temperature axis. And this is the weight. So because the weight is just this here. Now, what do we want to do next? So a forward pass. So think about a forward pass. This B1 and B0 is what we have initialized. So we just try to feed in all our data into the formula, and we need to get some y at. So in that case, we want to create some kind of method here. First of all, let me put compute error. I'm going to do everything here, compute error. So in the compute error, we want, I think we did classes the last time, and of course you understand what this self is. Oh, I think I made a mistake here. I didn't initialize the constructor. Sorry about that. Initialize the case, but eventually find out. Yeah, so this is the constructor. Once you initialize the class, the weights are initialized immediately. Now let us create the error. Of course, to compute the error, because if this is the error, we need to calculate y at, right? And this is our y at. Y at is just beta 1 times x plus b0. Good. So now, what do we need? We need to initialize the error because the error, we have to be adding it for every sample because if you look at, this is for one sample, we have to sum it for all samples and we get the average. So at least we need to initialize it to be 0, right? And we have to loop. We want to loop. So these points now, they will be the data set. So it would be, for example, x1, y1. That is the minimum temperature for the first sample, the maximum temperature for the first sample. This would be x2, y2, and on and on. So here now we want to loop through that sample, right? We want to loop through the whole through the whole length of the point. So, and of course, the points here will just be our the combination of this this minimum and maximum, that is predictor and our label. Now we will loop through all the points, and then we want to extract each of the samples because it will be a 2D, it will be a 2D array where the first sample is the predictor, and the second one will be the so we have to loop through it because Python starts with index 0. So what it means is that this one will always be as first index, this one will be at the this one will be at the 0th index, this one will be at the first index. We just want to pick the x and y that is for each of the same way. We have our y be equal to points I and this will be I and 1 because now we want to want to print the second one. So now what do we want to do? So let us our y at, which is just this formula, very straightforward, b1x plus b0. So that is just what we will be here. We just say y at y0 equals to self b1, which is what you see here, times x, because we have extracted one of the points, plus the bias term self b0, right? And now let us calculate the error. the total error, we would always be summing it. Remember the last time we talked about to sum error, we can use this plus or equal to y minus y all square. So I'm just implementing the algorithm, nothing more. Something like this, because this is the formula for the error, y minus y power all square. So this is what I'm just implementing. Sorry, this is supposed to be y at and all square. Now, so we have to, so if we want to return everything when we are done, because here we're only just summing, here. This is just what this guy is doing. Remember, we want to find the average cost of over all the samples, so we have to take the average. So when we want to return, we can just return the total error divided by, the length of the points. So remember, this point is the complete data set. So it's going, so let me give an example. So whether you use length or shape, or I think it's still going to work. For example, if I say length of extract, I think it's so you can see. So it's just going to extract the first, all the examples. And now we are done with this up to this point, right? We are done up to this point. Now we need to calculate our gradient, right? Which is very important for the update, because we want to update the parameters. So we'll create another method called, excuse me, self gradient. So the gradient is this formula. And I quickly, for some of us that understand calculus, sorry, I just have to share this. So this is how, this is how we derive the formula. We want to know how, okay. Oof, yeah. Oh, thing is messed up. Let me open it again. Yes, so the question is, how do we find this? How do we calculate this derivative? Now, if you look, this is our linear function. This is the loss. I mean, this is supposed to be cost, J, not L, but it doesn't matter because already you know this and this, they're just the same. And we want to kind of adjust the model, find the derivative on the bias, find the derivative on the weight, which is B1, and find the derivative on the bias, which is B0. So we just want to nudge. So we want to, when we want to know how much, we have to nudge B1, because it has to go in the direction of what we would expect, right? And also, if you use your, this is just very, it's just the very simple chain rule. Yeah, very just function of a function. I mean, you have your L, you want to nudge it with respect to your weight, just use this, chain rule. And in the end, if you just, simple calculus, you would know that the derivative of this guy is just here. And the derivative of this with respect to B1, if you differentiate this with respect to B1, this will go and we are left with X. So once you do your math for your weight and bias, so we are going to implement this now. So yes, so now let us implement our step gradient. So what do we need? So what do we need for our step gradient? We're almost done. What do we need for our step gradient? We need, we need to initialize the gradient, because you know that the weight, the gradient has to change, right? So we have to initialize. So we have 0. Then we just want to extract our n, because our n is, you would also, it doesn't matter, but we just want to extract n. Our n is just float. Oh, I think here it's also nice to add float, because if the length is, if it's an integer, it's going to try an error like that. So it's always good to work with, the same data, type something, because it's float. This random number here is float. So we should keep it as float. Yes, so now let us just, the length of points, which is the all the data set. And now let us look through all the samples, because we want to find, the derivative, based on each of these samples. Then at least this is stochastic gradient descent. So by next week, we would also talk about batch. We can do it in batches, but today we are sticking with just individual data points. So we will do the same thing quickly. I can just copy, and because we need to extract our X and Y for each of the data points, right? Yes. And now what we want to do is we will still calculate this B1, because in the end, do I need to? I think I'm even repeating things. I think I could have, okay, because we have to do it. Okay. So I have to retype because I didn't explicitly write a function to calculate y hat. It's just in this error. So, but I mean, it's just straightforward. We just need our y hat. So here, we just quote this formula. For B1 gradient, we type this. We have 1 over n sum of this, and yeah, it's very straightforward. So now let us find the gradient of the B as this gradient, because we have to update it. So in Python, if you don't initialize something and you want to update, it's going to say error. Yes, so this is what we want to update here. This is what, so first I think we have to find, so this is the gradient, then we'll update. So this formula is also very common to update gradient. It works in a kind of gradient descent, and we use the negative because we want to push this parameter to the kind of global minimum. We want to ensure that the parameters that would minimize this cost, we want to push this cost down, because if the cost is high, our model is not learning. So we want to push this. As we are pushing this cost down, then our model is adjusting very well to fit at least to the data. So now let's just quickly code this 1 over n summation of this. So we just have, we have 2 here, we can just bring it out. That's 2 over n times y minus y hat. I mean, it's just what you see in the formula. So square. No, I don't think there is square. No, there is no square. So we remove. So for the B1 gradient, I think it's just the same formula. We just add x because you know that the formula here, if you look at it, formula here is there's an x for the B1, but there's no x for it. So we just add x. Probably before so I think that's just it. So we have, this is the formula for the gradient. Now we want to do an update, right? Because we just want to keep adjusting this gradient, these parameters, the B1, beta 1, and the beta naught, using this this gradient descent update, this formula. So we have a parameter called the learning rate. It's also a hyperparameter. So once we put the gradient here, multiply by the learning rate, then we notch beta 1. If beta 1 is positive, beta 1 would reduce. If beta 1 is negative, beta 1 value would increase, which is what you see here. So we are just trying to adjust these parameters. Yeah, good. So now we can now do the update, because here we have calculated the total. Here has to be the total, gradient. Yes, and here all of this. I've done this here. Now let us do the update. So update, we have to update set B naught. Set B naught here, we just apply this formula, simple. B1 minus blah blah. So here we just be self dot B naught minus the learning rate times the B naught gradient, because that is what we have calculated here. Same for B1, because there are different parameters. We have to do the updates for different parameters. Set for B1 as B1 gradient. So the learning parameter, this parameter would, let me just type it in full. Learning rate. Here should be learning rate. So now we are done with the update, right? And I think that's just basically it, because when we look through this function, so we have this function that computes the error here, right? We update the error. I mean, we find the gradient, and then we update the parameter, and we just iterate. We continue to do this process. So what it means is, if we update this beta 1 and beta naught, this beta 1 and beta naught would now replace this. Sorry, I think I have to change this because it's somehow confusing, but sorry, I have to use beta. Then in the code, I used B because it's easier to type B than. I think for illustration, I should keep it uniform. Yeah, so it's, oh, what, I thought I changed it now. Okay, did I? Oh, okay, I only just changed this side. Sorry, because it's also confusing me. So yes, so everything looks good now. Yeah, sorry for the, yeah, it's just when you see beta one, you just know it's B1 or, but from this formula here, you should know already, like beta B, just use it for illustration purpose. And now the purpose of this update, once we update these two parameters now, that is what we will now use to complete the next iteration. You see, for the first iteration, this B1 and B0, they are completely random because we initialize them here, random. And now when we begin to do the update, the learning process, because now the model is now adjusting, kind of, because we want to go close to the original value. And, as the weights are updating, they are getting new values and, in an iterative scheme. So now let us write the train method. So it's a function that will combine all of these methods together. So we call it train self. I think here we have to put the point because we need the data points, right? We need the learning rate, this learning rate parameter. We need the learning rate parameter. Yeah, then we need the number of iterations. How many times do we want like how many times do we want to loop? Like, from what I just said now, we have to keep updating, right? And then, so let us just print. So let's print, we print the starting gradient. Then you will see how this gradient is reducing. So because first we start with the bias, then we go to the weight, the first index, the error also the second index, then dot format. So we can just, there are just better ways to represent this. You can also use the F string, right? We have the self B1, and we have the self complete error. So we want to complete the error at every step, and you will see, yes, I think this is done. Now let us let us print that our program is running, dot. And now let us just, do the forward pass and the backward pass for I in range, because now we are looping through the number of iterations. Remember, we are not just doing it once because we want the model to, to keep on learning as far as I'm concerned. So what we just do is we just, because the compute error, the step gradient, yes, so yeah, so we do the compute error first. And of course, we have the point. We have the learning rate. We have the learning rate. Oh, it doesn't have to be. I think it's supposed to be step gradient here. Yes, complete the error. Okay, we only just need the error for just to print out. Yeah. So because, yeah, but for this is where the O forward, because the O forward pass, this is the forward pass. This is the forward pass. And here is the gradient. This one is the gradient for B0, and this is the gradient for B1. So what we just want to do is, yes, I think that's just it. So we do the forward pass, why not? Then we get the gradient, which is very important to us. Then we do the update. That's all. Over here, we just want to calculate the error. Yeah, this is just the purpose of the for returning the total error. So the total error will give us an idea of how well the error is dropping. And since already here we have we have calculated the gradients directly from here, and we are not using any inbuilt library. We have to code our gradient ourselves. If we go into more sophisticated libraries like TensorFlow or Torch, PyTorch. You just get the error, then you can do some kind of, just write some dot, grad, and it's going to calculate the gradient. So now, I think that's just basically it. Then we can just, print out something like, if the iteration is less than, if it's at every 100 iteration, I want it to print the loss for us after iterations, and the error. I want us to see the error, and you see how the error would be dropping. That's format I at every steps. Then here we just put the complete error. Yeah, so the complete error, the point. So here we start, we see, and here we just end. So I think I can, okay, sorry, this should be self. I think I can also just copy this guy here then, so that we can see the end of the whole iteration. So after, we have the B1, and we have the format. I think, so here I think we should also put number of iteration. After a certain number of iteration, so here now would be after B1 is 1, then 2, then just keep it at there. Yeah, sorry I'm fast, but we can always still go through it, because we'll still be using this code tomorrow to continue for the logistic regression I plan to do also. Yes, so we print, we want to see the error, the number of iterations here. Oh, sorry, this is not supposed to be so. This is supposed to already have done that. Number of iterations, that is here. We have the B0, B1. We see how the parameters are changing. Then we see the error. And that's just it. And we can write another method that will predict our results, because.
Sorry for the break. Due to technical reasons, we lost the last 15 minutes or thereabout. So from where I stopped, so we can write a method for predicting our results. So after the fitting the model, on our training set, so we want a method that would help to predict our results. So it's very easy. And what we want is, we want to predict the y-hat. We already have our weight that has been learned. We multiply it by the test set or the data point, and then we multiply by the bias parameter also that has been learned. And so what we want to do is we want to return, right, y-hat. So I think we are practically done, and we would run this. So the next thing would be to prepare our data set for training. Already we have our X train and Y train also in form of data frames like this. But if you look at our implementation here, we implement it in such a way that a point is a combination of both X and Y, right? And it looks like what you see here is that we have a 2D kind of array where we access each of the entries by the index I, that is from I1 to N, that is 1 to, in this case, 95,000 or thereabout. And for one data point, we'd want to extract the feature at index 0 and the label, which is at index 1. So what we can quickly do is to, we can, kind of stack, we can stack the training sets and the labels together. So here we can just extract the values of the training set. But usually you can also work with data frame, depends on how you implement the your program. So here also we want to extract the values and sorry, y train dot values. So also same for test set, we want to extract the values, and also for y test, we want to extract the values. So now what does this mean? So by doing this, we no longer have the S test and Y test as data frame, but now we have them as just list list of the entry errors. Okay, probably I didn't run it or something. Let me try to run it again from here. Okay, yes, yeah. I think somehow yeah. So, okay, this is our X train, cool, as data frames. And now let's go back to, okay. Yes, X train. Y test, it says Y test dot values, non-attribute values, then okay. So far we have not, okay, yeah. Sorry, we have to, yes, here. Okay, I think now we can have a look. Okay, here is supposed to be Y train. Yeah, it's yeah. So now it looks good. And initially we had X train to be like data frame. Now you can see that X train is now list. So the list of the features. So you have the list in a list, and also for the Y train, for the first term, as you can see, also we have the features, right? And we have, we have the labels, and we have the features. Now let's proceed to scaling. Well, usually it's not the case that we want to scale from data frame. So here we want to scale our data, because most of the times your features would not lie in the same scale. They won't lie on the same scale. So, but in this case, we are using one feature, so it's safe to say that. And also, the feature and the target variable, they kind of lie on the same scale, because temperature, whether it's minimum or maximum, they also lie in more or less the same scale. But we are going to scale this for practical purpose. And usually scaling can also improve the model. From sklearn, I think, because just to keep the model short, the implementation short at the time, already I wrote the code somewhere, so I just paste. So what we're just going to do is to import the standard scaler from the sklearn library. So what this would do is to scale the data, to center the data around mean 0 and standard deviation sigma. So and yeah, whatever. So we also need the numpy array to stack this. So first we will define a scalar x for scaling the x, the features. Then for y, for scaling the labels. And now what we're going to do is we want to define a new train set, which is scaled set. And we already have our scale s, then we will fit it on the training set and at the same time transform the training set. And also for the y train, we would also fit it on the y train. Then here we reshape y because we want to ensure that y, because here, let's print the shape of y. Yes, it's still fine. So it's still going to work, even though it's not reshaped. But usually it's the case that, y might just, y might not have any dimension. It's just, so this, we have to add this extra dimension. So in this case, it looks like we don't have to scale here. yeah, everything looks good. So we scale, and now once we have scaled it, we will now stack it. So we want to stack them column wise. So we use the NPH stack, and as you can see, it stacks array sequence horizontally, that is column wise. So what it means is that one of these data points now, as you can see, if you pick the first row, then the first entry would be the feature, and one would be the label. So here we can just run this. And as you can see, just here, we try to print out one of the points for the first, for the first entry we find. So during your training, so let us print from 1 to 5. Now, what you find is this is the first 5 points. So this is 1 point, and this is the feature. It's going to be extracted from here. This I is just this, just means that we are going to something like, you do something like this. Oh, so it's going to throw an error. So for 1, 0, it means we are taking the second point and the first point, which is the feature. Here we are taking the first point and the label, right? So, and we can also print out the shape of our new array. So you can see we have kind of 95,232 by 2. So each of these rows have both the feature and the label, right? And now let us train our model. So to train our model, if you look at our model, we need to define the learning rate, we need the points. So I think we need these 3, the points, the learning rate, and the number of iterations. So those are the parameters, those are the arguments we are going to call into the fit function method. Here, we don't need to initialize, we don't need to put anything here because just initialize this at random. So now what we are going to do is to train our model. It's very straightforward, also to keep the time short. So we have our learning rate, as I talked about. We have the number of iterations. We want to iterate for 1,000. We call our model custom linear regression. So I renamed this from linear regression to custom linear regression. This is because the inbuilt linear regression in the sklearn library has the name linear regression. So we have to use a custom linear regression so that you don't run into problems when you want to use inbuilt libraries to build your model. And we just put our points, which is what already we have, our learning rate, our number of iterations. So these 3 arguments is what we, fit into what we, replace this argument here in the fit method. So now let's just quickly run our code. And now immediately it starts to run. As you can see, this is our bias initialized at the first point. This is our weight. As you can see, the error is 0.65. And here you can see the error dropped after the first pass, the first iteration. You see the error is now 0.6. It drops to 0.23, it drops to 0.22. And you can see it's still dropping. So while it's dropping, let us prepare our test, what we are going to use for our test set. So first of all, we want to also scale because in the test set, if you remember, we have to also scale the test set because we scaled the training set to build our model. So it would be nice to keep both the training and test sets on the same scale. So using the scalar X we defined here, if you remember, and remember we fit it on the training on the X train. So we are going to use that scalar that we use to fit the X train on the test set because we don't want to define a new scalar. We want to use the same scale, that is the mean and the standard deviation, right? So that we will keep so that we will not introduce some kind of inconsistency in our model. So now the model is done training. We have our initialized bias to be 0.44. We have our initialized weight to be 0.40. At the end of the training, we find that our bias is very close to zero, about 7.49 exponential minus 10, exponent minus 10, which is very small. It's just approximately zero. And we have our weight parameter to be 0.87. You can see how it adjusts from 0.4 to 0.87. And you can see our starting error was 0.65. Now we find our ending error is 0.22. Now, let us scale our training set. So like I said, our test set, we take the scalar and we transform it. The difference between this and this is the fit. In this place, you notice the fit transform. You use the fit transform only on the training set. And you use only transform here on the test set, because we are not, we are not trying to recompute new parameters for scaling. We want to use the same scales, right? Otherwise, it would kind of introduce, some, let's say, data leakage, because now we are not consistent with how we scale our data, and we can't even know how well our model performs. Same thing for the white test. We just do the scaling, and here I don't think we need to reshape, because already our white test is in, as 2 dimensions, so we can also confirm. So it's always good to check the, the dimension of what you're, so you can see it's okay. If you're having just only this without this one, then you might have to, reshape it in this way. Now, when we are done scaling, we just, predictions. Remember, the prediction would come out in also scaled version, because if you look at the model, if you look at this, I think there was a place where we printed out. Okay, yeah, let's try to, yes, over here, when we print out the first, let's print out the first 5 points. So you can see in the training set, the values have changed from what we have before. What we had before was something around like 20, 21, and the maximum temperature is 31, 30. Now, because we scaled it, remember, we used standardized scaling on centered around mean 0 and standard deviation sigma. So now the values have changed, but we don't want these scaled values. We want the original values. So after prediction, here we just call the model.predict. Remember, the model.predict method just returns the predicted model. And here, if you notice, we just use this simple multiplication term. This is because our x is just, we have one feature, and our scalar is, our weight is also just 1. So here it's not really sensitive to the multiplication, because at the end of the day, if you multiply a vector, a matrix by a scalar, it's just going to broadcast. So each of these x values would be multiplied by the weight. But in a case where we are working with 2 or more features, and then you have to be careful, because now our weight is no longer just a scalar, but kind of vector. And you would want to do some matrix multiplication, which is dot product, and it has to be you have to be sure if this dimension, if the dimension of the x and b1 is properly computed, or kind of imputed in the in the dot product. Sometimes you might have to do some transpose. Probably you want to define your bias as exactly as it's going to make the matrix multiplication possible. Or if you want to use maybe a row vector, then you have to transpose, or you want to use a column vector. Otherwise, you don't want to transpose or something. Just ensure that the multiplication has to be possible, especially these 2 terms here. But in this case, it doesn't matter, because it's just one feature. So so when we are done, the prediction would come out in scaled values. We can also check it. So let us print out our prediction scaled, because the output is scaled. As you can see, 0.5 minus 1.1. But we don't want scaled value. We want, the prediction of the maximum temperature. Now, what we are going to do is, remember when we transform the data set, we have to do the inverse transform. The inverse transform would take the scaled value back to its original form. And remember, it is the y that we want to, we are predicting. So we need to, that is the maximum temperature. So we need to take it back to its original form. And then we just use the inverse transform on the predicted, on the predicted values, which are scaled. So we can also remove the shape, because also this is has 2 dimensions, and so it's fine. So when we do this now, you will find out that the value is now scaled. So we can even confirm when we print the predictions. When we print the prediction, so you can see now it goes from 0 point something initially. Here, let me print again. So the 0.5 initially is the scaled version, and now when we inverse transform it, it goes back to its original form. So just be careful so you don't work with scaled value. So now we are done. Let us stack it together. Remember, for our model, we don't even have to, our test set already is properly, so we don't even have to, we don't even have to reshape this. Yeah, because the test set is properly reshaped, and when we are reshaping, we are just adding this extra, dimension, and it keeps the former. It ensures that we are just adding this extra 1 dimension, and this keeps the former, dimension. So if you have a vector of, let's say, 10, now you're going to be having 10 by 1, right? And because our test shape is just the same, I don't think we need this. Yeah, we can just, directly stack it to our to the points that we need for our model. So let's run this. Yes, so now everything works out, and now let us now train our model. I mean, so now we already have the okay. Okay, so what am I saying? So already we don't even need, so already we have our results, yes. And now let us compute the R square. So there's what we call R square. Oh, I think okay. I think, yeah, so I think I was talking about training on this, I think this part shouldn't, okay, I think it's mixed up. Okay, it's not mixed up because the predict, okay. I think I should take this out of this place and just paste it here. So we have our scaled data set, and we have our predictions. We invert it, the Y test, the Y predictions, okay. We just kind of stack them together. And so now so we stack them together because, yeah, we want to also write a function that would help us calculate the R square. So the R square is just also a nice metric that helps us to, that explains the variation. So it tells us if the variation in the data set, is explained by the relationship. So that is the feature and the, target variable. So, and it's just, here we know the sum of square error, which is, as you can see, the difference, the difference between the true value and the predicted value, which is called the residuals. And we take the square, we sum it. And, here we just take the sum of square total. At least we try to also sum the difference between the true values and the mean of the target values. this is the label, the predicted values. These are the means. I mean, this is the mean of the target variable, and we just we divide, take the just the ratio, we subtract from 1. So the closer it is to 1, so if sum of square residuals, I mean, if this ratio is 0, of course we have 1. In this case, then they are the same, right? And we can say that the variation is perfectly explained because we have our sum of square residuals, which can hardly be 0. And then, so if the residual is very small, that is because we want to ensure that the residual is so close to 0. Sorry for the break in transmission. If you want to ensure that this, your model is performing very well, then the error has to be so close to 0, right? And if this is 0, you have 1. That is, your model has a perfect fit. And the larger your error, then you know that the bigger this value, and then the farther it is away from 1, right? So let us run the R square. And now we can just, we can compute the R square. So by computing the R square, we just want to see also, and also we want to plot the predictions on the, on the original label. So we just call this function. And the points, remember, the points here just means, we want to predict. So we call the point. Yes, and here we pointer scaled. So do we need this? I think it's just a mistype. So we have the Y true. Okay, the Y true already is what we have. Okay, no. The Y true. Yeah, sorry I think I have to do some corrections. We want to predict. So do we have to predict again? No, I don't think so, because already we have done our predictions, right? I think this is what we need here. The Y true. Okay. Yeah, we don't even have to do all of this actually. So we can just put the Y true, and we can put the Y predict. I mean, it doesn't matter. It depends on what works for you. And so here we know our Y true here. And, remember our prediction is here already. So we can immediately just, so this is not needed. So if I would do this, then we don't have to do this over again, right? So it's of no use trying to predict the model again, because we have done that here. Yes, so I think I wrote the implementation before I called this prediction, so it's fine now. So we have our true label, we have our predicted label, and then we take the sum of square residuals. We take the sum of square residuals here, same, the mean, and yeah, we do this. So let us run this. And now for the R square, we calculate the R square. And remember, when we predicted our results and our Y true, we just want to see how close the prediction is from the true value, right? Okay, so Y true is not defined. Okay, it looks like we did not define Y true. Probably because, okay, that should be Y test. Because already we, yes, there's nothing like, so let us put our Y test here. And let us confirm if our Y test is valid. Yes, our Y test looks good. And also our predictions. Yeah, also perfect. So now it should work. Yes, so now we have our model. You see, we have our linear model, right? And the blue points are the test data set, and we have the straight line, which looks not bad. At least we have the straight line go through this scattered points. And the question is, what is the model? So what are the parameters of the model? And simply, you know that the linear model is just, you have some y equal to beta 1 plus beta naught. So it means that your beta 1 and beta naught will be the parameters of the model. So if you want to visualize also, we saw that here, B1 and B naught. So you can just print the parameters of the model. So we have the parameters to be, that is the weight. The weight parameter is just, you can print model.b1. So that is for the weight. And then for the bias, that is B naught with B1. So these are the parameters, this will be the parameters of the model, as you can see. Okay, I went to type print in. Sorry. Yeah, so yes. So now we have our weight. We can just, we can just put it to 4 decimal points. Yes, okay. Okay, I think this should be. Okay, we have to use the F string. No, yeah. I think I can just, easily just do this. So yeah, we just want to print out for printing sake, nothing more. So here's the B naught. And yes, here we can, yeah, I think I just, so here we have our weight, then we have our bias parameter. So this will be the parameters of the model. So if you want to write this model kind of, in an explicit way, find out that the model, the parameters would just be, because you have B1 times X plus B naught. So what you're going to have indirectly would be 0.8781 times X plus 0. So more or less like the bias is just canceled out, and we just have this linear function here to be the model. And this function is responsible for this straight line, for fitting the model, for fitting the data. Thank you very much. And yeah, I hope you can practice more, and also use the inbuilt libraries for solving problems. But you can also go through the algorithms and also the implementation, and so that you can understand how it works. Bye.